The first one, C2H4, that is, what are the Vesper geometries for mustard gas and the following. Now, we're ending with mustard gas for a specific reason. We'll talk about that in a minute. We're going to start with two ones that are a little simpler, C2H4 and CH3OH. And we can go on the internet and we can go to YouTube. We can find a visual of this, the molecular geometry that is. So we'll show this to you real quick.
Now, the molecular geometry at this carbon atom is tetrahedral because carbon has 4 bonds and no pairs. At this particular oxygen atom, the molecular geometry is bed. It has a similar structure to water, which I really should have drawn it this way. It looks like this. Water, on the other hand, well, water looks very identical too. As you can see, it has that same bed geometry. Carbon, a hydrogen, and it has 2 lone pairs. So it has like 4 groups.
Okay, we're going to talk about the sp3 right now.
The carbon atom.
It's kind of new today. So if you look at the handout that I gave you when you came in, we have the 3 examples. Now it can go to the D as well. It's not limited to the S and the P. Why do we typically only talk about the S and the P? Or carbon-based life forms. So when you go into like medicine, you're going to typically just see carbon. So if you go to chemistry and college, you take organic chemistry, it's basically study carbon. You'll see it there as well. So you have the sp3. Does everybody see the sp3 there? And you have the sp, then you have sp2, that is. Then you have the sp. The best way to really understand this is to kind of go from the simplest one to the most complicated one. So let's look at the triple bonded one. So everybody see the triple bond? This triple bond corresponds to the handout that I gave you yesterday. When we're looking at these 2 different bond types. You got the alkane, the alkene, and the alkyne, right? So the alkyne has got this triple bond, and that's going to be the sp. Now it's P because it's linear, right? It's px. It's on the x-axis. Does that make sense? Yeah. That's why it's going to be sp. So if you see something linear, it's most likely going to be sp. It's only going to be bonded on that x-axis. Now if you see something that's sp2, you're typically going to have a double bond associated with the carbon there. And you're going to have the px and the py. So the px is going to be our horizontal axis, right? You can see the px there on the horizontal axis. And then the py is going to be up and down. So you've got that px, py possibility. Everybody see that? Now the most complicated to look at one is the sp3. And they've given you a drawing of that here at the bottom of the page right here. They can show you the px, the py, and the pz. All 3 dimensions are playing a role. And that's typically where you have a single bond all the way around carbon. Now at the bottom it says, the concept of hybridization was introduced because it was the best explanation for the fact that all of the CH bonds in molecules like methane were identical. So can you mathematically prove this? No, you can't. This is just a concept to try to explain what's going on a little bit better. That is, the bonds are identical between the carbon and the hydrogen. It's just another way of explaining the px, right, that the molecule is linear. This px is linear. So you could say hybridization sp, and somebody would know you're talking about like a linear molecule. This is important when you're trying to solve problems quickly associated with medical issues. Mustard gas significant? If you go back and you look at history, World War I is considered to be what?
The worst.
It was the first basic chemical war.
I know that they made it it was unhonorable to use gas because it wasn't a main way.
No, that's World War II or after. But the first World War, it's really considered.
Well, I know because they were saying it was using gas was like unthinkable or something like that, but like Germany ignored that and kept using it.
Right.
Or something like that.
Yeah, Haber, he was the one that worked on this. So the point here is that World War I was considered to be, or is considered to be, the chemist's war. It was like the first war where chemical warfare came into play. Mustard gas was introduced, and the thing about mustard gas is that if you have on a gas mask, it doesn't matter. It can get to you through your skin. So you're still going to die if mustard gas is used. That's why people are freaking out about it, because several weeks later you die due to exposure from it. The gas mask didn't protect you. It doesn't matter if you had a lot of clothing on too, it could still penetrate through your clothing depending on how close you were to it. Now, with mustard gas, there was a bomb that was dropped. We're going to look at Wikipedia and read that so we don't... The modern era of cancer chemotherapy can be traced directly to the German introduction of chemical warfare during World War I. Among the agents being used was mustard gas. So if we go on down here to the bottom, it says that there was, a year into the start of the research, a German air raid in Italy led to the exposure of more than 1,000 people to the mustard gas bombs. Basically, they did autopsies on the victims, and they found lymphoid and myeloid suppression had occurred after exposure. So they were looking at the certain types of cells, these somatic cells, that lost their nature to divide fast. And that potentially led to this being used on certain types of cancerous cells. So mustard gas actually killed cells very quickly. They noticed this in autopsies, and they were like, let's try to use this, manipulate this to where we can have some type of tool to kill cancer. So chemotherapy originated from mustard gas. That's a kind of important concept to know, because you hear about cancer and chemotherapy and radiation treatments. You should kind of understand the origin of it a little bit.
During that same period, the U.S. Army was studying a number of chemicals related to mustard gas to develop more effective agents for war, and also develop protective.
Over the years, chemotherapy drugs have successfully treated many people with cancer. Long-term remissions and even cures of many patients with chronic disease, treated with
Combination chemotherapy to do the trick. Now, if you turn the page over, you'll see where it talks about the immune system. And the immune system is capable of recognizing cancer cells. It says the immune system consists of a large number of different types. Somebody read that? Go ahead, Adam.
Types of immunity, non-specific and specific. Further information on the topics in this page can also be found in most introductory biology textbooks.
Okay, so this has been proven in the lab that your body can, the cancer cells are recognized and attacked because they differ from the normal self from which they arose. So this has been proven in the lab. Now, if you look over here to Science Daily, let's read here. They basically talk here that your body recognizes a cancer cell and then has an immune response that doesn't want to attack it. So let's read this and we'll talk about that. Who wants to read there? How about Cody?
Body that need to be protected. This result was obtained by the team led by David Klatzman at the laboratory.
So this study shows that during the very few days of development of a cancer, our immune system recognizes cancer cells not as abnormal cells requiring eradication, but as cells of the body that need to be protected. Now the question is, why is this? Do we have a reason why this might be the case?
Maybe the white blood cells think that it's not hostile and it won't do anything to the body.
Okay.
Which in a certain case, I guess, cancer really doesn't do anything to the body, but except for just spread. That's the only thing it really does, doesn't it?
Okay.
Cancer just caused from a bad reproduction of
It's
that cell?
just constant meiosis.
Uncontrolled cell growth, yeah.
Yeah.
Okay, can chemotherapy cause secondary cancers?
Yeah.
Yeah, it can. So let's look at that.
It's molecular geometry, and that'll help us understand the molecular geometry for the whole C2H4 molecule. When we think about valence shell electron pair repulsion pairs, we think about how those atoms are going to spread out in 3 dimensions to be as far away from each other as possible. So when we look at this carbon here, we can see that the hydrogens and the carbon, when they spread out, they're going to spread out in a plane and be as far apart from each other in that plane. We can also use the AXN notation to figure out the molecular shape.
So we talked about the AXN yesterday. You can look on this sheet and you'll see the first one linear is AX2.
AX3. And then N, those are the non-bonding electron pairs. So we don't have any non-bonding pairs on that carbon. They're all involved in bonds. So we're not going to worry about them. So that leaves us with AX3. So you could have either memorized that AX3 is trigonal planar.
So you can see it right here, trigonal planar, which is basic geometry, steric number 3.
Well, there's AX3, and that is.
It's got a 120.
Planar, and the bond angle is 120 degrees.
So each of these are going to be 120.
That's a molecular geometry for the trigonal planar. Let's go back. And
So both of these are trigonal planar. This carbon and this carbon linked together. I buy at Store Hope. Like, you got a cough drop you like to buy? Which one you like to buy? Which one? You like the Halls? Halls cough. Raise your hand if you like. Have you ever had Halls cough drops? Yeah, they got that menthol, or yeah, the methyl. It's the methyl alcohol. So if you go and you buy cough drops, you're gonna have methyl alcohol in them. Yeah. Cough drops use menthol. I actually confused it for methanol. Sorry about that. It has a 10 carbon base chain. We talked about the chains being R yesterday. That is, the chain of carbon is R. So the menthol, if you look right here, you can see the alcohol base on the menthol, which you're going to find in like Hall's cough drops. Now, methanol is found in a lot of different things, like you can find it for high octane. It's used for burning fuel, clean burning fuel. It's an important substitute for gasoline. It's derived from wood. It's unfit to drink, so don't try to consume any methanol. It's basically wood alcohol. So keep that in mind, that methanol and menthol are not the same thing. Formula. And now we're going to watch a little YouTube video on the hybridization molecular geometry for methanol.
We're going to discuss the molecular geometry
For C2H4, we just saw for the alkene, C2, the alkene, ALKENE, gave you this yesterday. What was the molecular geometry that they talked about in the YouTube video? Trigonal planar. Remember, it was 120 trigonal planar? Now, that one had the same 2 geometries. Now, if you go home and you're looking at geometries in the future for molecules online, and you see how they're spatially arranged, and you're wondering how they got that, it's coming from these geometries. These 15 different geometries. So the first one here is for the carbon and its tetrahedral. So it's not going to look like they're drawing here Lewis dot on a computer model. It's going to look different from this. It's going to look based on these geometries put together. They can do it better on a computer than you can draw it, because drawing it, this angle right here for tetrahedral is not going to be drawn as 109. It's hard to draw a 109 angle here unless you've got a protractor out, and they're not doing that. That makes sense? A computer can do it a lot easier if you program it correctly. And then the oxygen is bent. So you can see here it's got 2 things connected to it. It's got 2 pairs of electrons. So you go back to this one and you see bent, and you'll see it has 2 pairs of electrons and 2 hydrogen atoms attached to it. Do I see that? So this one has 2 different molecular geometries associated with it. Now in this video, they introduced to you the S3, S2, SP3, SP2, and the SP. And you can see that on the handout that I gave you today. This cannot be mathematically proven. It's just a way for us to obtain the concept. And the concept of hybridization was introduced because it was the best explanation for the fact that all of the carbon-hydrogen bonds in a molecule, like methane, are identical. Vesper geometry for mustard gas. You got your tetrahedral AX4 on this carbon. Same with this one. The sulfur is going to be bent. And then you've got tetrahedral, followed by another tetrahedral. Then we have our chlorine. It's considered the chemist war, the chemical war. The first war. The first war is where they actually started to use chemical warfare, and they dropped mustard gas, that is the Germans did, on a population. And the thing about mustard gas is that if you had a gas mask on, it wouldn't do you any good. It can penetrate through your skin and cause problems and like kill you. So mustard gas is very dangerous. Some images of skin exposure to mustard gas. And this kind of, wasn't good. People thought that if they had a gas mask, that would protect them, and then they came out with mustard gas, and you can see that even if you were clothed with, your battle gear, it still could get through that.
Drug was the predecessor of methotrexate, a cancer treatment drug used commonly today. Since then, other researchers discovered drugs that
Cells are?
any cell of a living organism other than the reproductive cells.
Right, so like your skin cells. So if we go back and we look at the definition here, it was noted that the mustard gas ceased the division of certain types of somatic cells whose nature was to divide fast. So in your body, which cells typically try to kill invading like bacteria or viruses?
White blood cells?
Right, the T cells. You ever heard of the T cells? It's like your immune system, right? Y'all familiar with that? So let's turn the page over and read about that. The handout that I gave you, if you turn it over, you'll see that it talks about your immune system. So who's going to read system description from Quest Cancer and the Emory Winship Institute basically says the cancer cells are recognized and attacked because they differ from the normal self from which they arose. Now they're attacked from the immune system, and it says right here, when an immune response is induced by the body, 2 types of lymphocytes are particularly closely involved: regulatory T cells and effector T cells. So let's read on there. Who wants to finish that up? How about Simon? I want you to read where I just left off on the Science Daily. Desire to be like an architect, or you desire to be a builder, you have to draw your plans out first. Like if you want to build a house, you have plans that you build so that you know what materials to order so you can build the thing properly. And that's the benefit of having molecular geometry. We can then visualize what molecule we want to either make or we want to break apart. When you go into medicine, there are different medicines that we try to develop that help cure various diseases. So up here, this is the simplest one. We talked yesterday about C2H4. Anybody tell me points? What is C2H4? C2H4.
And there's what's the 3?
C2H4. Alkene. Alkene. C2H4 is alkene. It's double bonded. So let's take a look at this and write down the molecular geometry. These would be notes.
Yeah, C2H4.
for molecular compounds. Now, this algebraic expression up here is what we're going to use to reference. You can see right here, he's using this formula, AX3, to tell you the shape. And it's next to this grouping. Now, if you look on the chart that he has here, it doesn't have all 15 listed, and it doesn't show you spatially what they look like. Now, it is very difficult to draw this in the 3-dimension. Why? That's true, but you're also talking about a 120-degree bond angle. Is it easy to draw a 120-degree bond line? No, you have to pull out a protractor. So it's much easier to do this on a computer. So most modeling now is done on computers. Very little is done on paper. We did very little when we were in college on paper because you could buy computer programs even at that time, which was like 30 years ago. Brendan? Gasoline. Where else can you find methanol? Menthol is not the same. Menthol is like C10. So menthol has 10 carbons. Where else would you find methanol? I don't think you can find it in meth. You can find methanol in
Isn't that medicine?
cleaner. No, you can't consume methanol. Methanol will kill you. That would be menthol. In a windshield washer fluid, you can find it in, you can see that very well, cleaners, turtle wax, antifreeze. There are 15 different Vesper geometries. And today we're learning that you can stick them together in various ways, and then you can get a 3-dimensional picture of what the molecule looks like. So up here, this one, for methanol, we have tetrahedral, and then we have bent. It'll be very difficult to draw this because you need a protractor to give you the various angles, but you need to know that they do exist. Now the first molecule, the C2H4, what were the geometries for that? Does anybody remember? We just watched the video on it, so it should be fresh in your brain.
Wait, what are you asking?
The Vesper geometry for C2H4. No, I just want to know what they were. There were 2 of them. They were the same. You should have drawn it. They said that the angle, I'll give you a hint, was 120. Trigonal planar. So the trigonal planar, or the trigonal planar, would be the geometry for C2H4. And if you have the sheet from yesterday, you'll see that C2H4 is called the alkene, A-L-K-E-N-E. So methanol, you've got more than one geometry. The last one we're going to look at today for your bell work would be mustard gas. So mustard gas is C4H8Cl2S. And there's a reason why we're looking at mustard gas. We'll talk about that in a minute. What I want you to do is copy down on the board. This is the Vesper geometry for mustard gas. So you have a chlorine. Does everybody see our 2 chlorines? We have our 2 chlorines here. We have 4 carbons, 2 are on the outside of the sulfur. And then we have the sulfur in the middle. So we start here with our carbon. It's AX4. So the carbon has 4 things bonded to it. So it's tetrahedral. You don't see any electron pairs here, so it's AX4. Does everybody see how the first carbon is AX4? Now the chlorines are not defined. If you look at the Vesper geometry, it's not defined. It's just attached to this long carbon chain. The chlorines make this thing very dangerous. Mustard gas is very dangerous. What war was it first used in? Anybody know? It was used in World War I, First War. Why did everybody? Why was everybody very concerned about the use of mustard gas? Okay, raise your hand. Anything else?
You can be very, it's very toxic.
Okay. Will a gas mask prevent you from exposure? No. So if you have skin or your clothing is not, I guess you would say, plastic lined, then you are going to be exposed to this. When I was in the military, we had our, I guess you would say, hazmat clothing we would wear in case of a chemical attack, and it was all plastic. If you put that on in the middle of summer, you were just like perspiring profusely. So if you get mustard gas on your skin, you can Google some of the images if you want. It's not pretty to see. So it makes it very dangerous because of the chlorines. These chlorines are going to attack aggressively, seek to bond and change things on you. What does N2 mean? Okay. Might know what the N2 is? Yes, dehybridizations are possible. We don't care about them a lot because we typically study carbon-based things. Like if you go into science, into a lab, you're usually going to make things that people can buy and sell. And the majority of those are pharmaceuticals. You can get into industrial chemistry where you'll see different dehybridizations, but the majority of organic chemistry, medicine, is going to be just the S and the P. So does everybody see that the PX is associated with the horizontal plane? Now let's look at the double bond there. Does everybody see the double bond? In the double bond, you have two planes. I've drawn it on this diagram here. That's what it looks like. And you've got the PX and the PY. So if you were to kind of turn it just a tad, you can see you've got those three circles. And if you draw a line through them, you're going to get a PX and a PY. The double bond looks different than the triple bond. Does everybody see that there's a difference in the look of the double and the triple? So we would explain the double bond to be sp2 because you've got the px and the py planes. So if you go into geometry, it's typically what you talk about, px and the py. Right? Make sense? Therapy cause secondary cancers? Oh, it can? Yes, it can cause secondary. It can cause secondary cancers. And what is typically the reason for that? Anybody know? Why it causes secondary cancers? But what we're trying to do, once again, we're trying to take things like mustard gas and figure out what the molecular geometries are, and then design molecules that are better at attacking things we don't like. That would be our plan, right? So up here, chemotherapy can produce second cancers. And we talked about what was the reason for that. And up here they tell us, I'm not telling you, they're telling us, that the research says that if you have it says here, the risks get higher with higher doses, longer treatment time. So when they give you a higher dose of chemotherapy, you have a greater risk for secondary cancer. Now what they're doing today, they call it like chemical treatments, where they're giving you multiple different types of chemicals, so you're not just being exposed to one. And do you understand why that is a pretty good idea? Why is it a better idea to expose you to a lot of, I guess you would say, more dangerous thing than just one dangerous thing? You can start building resistance, but let's go back and look at alcohol. Can alcohol cause cancer? Right, alcohol can cause cancer. Do you think if you drink one drink a day compared to somebody who's drinking like 12 drinks a day, who's going to have more likelihood of getting cancer? Yeah, 12 drinks a day. So the first step the doctor's going to say to you is, what are you doing that's most likely causing cancer? And if you say, well, I smoke, what's the doctor going to say? Yeah, that's probably the number one thing that you can do. Doctors will tell you is quit putting things in your body that are known to cause problems. Now, if it's a genetic cancer, those are much more difficult to treat. Genetic cancers, really the only hope right now in genetic cancers would be like genetic manipulation of your offspring so that your offspring don't get that cancer. Because if you go into like science and you research bacteria and you put genes in there, it's very difficult to get the genes all into your body to prevent or to cure the cancer that's genetic that you are facing. Yeah.
Isn't it called remission when like you have cancer and then all of a sudden it's like gone?
Right, that they can't detect it.
If we don't have okay, so somebody has genetically advanced cancer, like let's say somebody has breast cancer and somehow you're cured, like is that like a mistake that the doctor did, or like I don't understand how that just happens, how they accidentally like fix it.
Okay, well, if you look at the backside here where it says Cancer Quest, they tell you that your body is capable of killing cancer. It says the cancer cells are recognized and attacked because they differ from normal cells, from the normal self from which they arose, right? Does anybody remember the type of cell that attacks cancer? Remember biology, what they call those?
Oh, is it the
All right, let's read.
Of cancer, our immune system recognizes cancer cells not as normal cells required eradication, but as cells of the body.
Says that when your body first recognizes cells that are cancerous, the body wants to not kill them but protect them. And the question is why? If you've been smoking for, let's say, 20 years and you don't have any cancer, what's the reason for that? Anybody know? What organ in your body detoxifies things? What? The liver. Right. So, unfortunately, your liver, or your body's ability to detoxify things has been very strong. But the problem is, after a while, like if you're drinking 12 drinks a day, alcohol use, and you get cancer, it's because your liver has, met its limit. It can't, detoxify that anymore. And so the body says, okay, we got to set up a place to the side and isolate this substance. So that's how many researchers are viewing this. They're saying, okay, the cancer is being protected because they don't want it to grow inside your organs, and eventually it does if your body is being exposed to something. So step one, if you have been exposed and people think you have cancer, the first thing you should try to do is find out what caused it. If the doctor says or asks you a question, do you smoke, and you say yes, doctor going to say stop smoking. The doctor says you drink alcohol, and you say yes, and how much you drink, you say 12 drinks a day, doctor going to say stop drinking. Doctor's going to advise you to try to eliminate things you've been exposed to that cause cancer. So if you go to, let's say, Home Depot, and you go to the paint aisle, there are a lot of chemicals that are cancerous. You could be working in a factory, and that could be the cause of maybe some of the cancer that you have. And you probably need to get out of that environment. But if it's none of those, then it's going to be most likely genetic, and that is going to be the most difficult one to cure. You're going to have a difficulty with the chemotherapy as well because of the side effects associated with that. They say the secondary cancers are the hardest ones to treat, so if you go back up there and you look at that. But we're working on it. Hopefully one day you'll continue to find interest in this and come up with a new molecule. But the new molecules are produced by these molecular geometries. This is why that's important. So just to tell you about molecular geometries and not trying to explain to you where the importance is on this, where research is still being done, we have not found a cure for cancers because there's so many different new things that come out. Anytime a new product comes out, most likely somebody could be, cancer exposed to it.
But question, every time somebody comes out with that they have a new cure or whatever for cancer or a sick disease that has a lot of money to it, they end up getting killed.
Right. So it's kind of like you are being treated for X and it causes Y. Have you watched the commercials on the news channel for various new chemicals that come out? This will help you with X, but these are the Y side effects. Right. So the best thing to do, obviously, is to try to eat right and exercise. There's a new, I I guess you'd say, alternative locally, you've heard of 25 again, hormone replacement therapy. That's relatively new as well. People are always looking for an edge to try to, stay young. So we really don't know if supposedly the doses are small, but if you're not eating right and exercising, they might have to increase the doses. That could be a problem. Budget for next year doesn't have any money for textbooks, and the point here is that you can search the answer for this question here.
What was the governor that was going to be elected that adopted all the kids?
Devin?
Are there actually some kids?
I believe so, yeah.
I don't think they are.
So it says, what is the assumption of the model? And the answer is right there. So you can search this. In antifreeze, on the label, Jack, on the label antifreeze, you'll find that it has methanol in it. Now methanol, if you consume it, it damages your nervous system, which would be true for dogs as well. You don't want to drink this stuff, very bad for you. It can kill, so it's obviously deadly. It's considered to be wood alcohol. So we're going to look at the molecular geometry for methanol. What? Trigonal Planar, very good. So it just had one. Now, Versace, very good. Now up here, this one has how many?
Four.
No, this one has how many molecular geometries?
Five.
Raise your hand. Andrew?
6.
No. Jimmy? No.
5.
Andrew? No.
8.
No. James has 2. Can you name them for me? Tetrahedral and bent. Now if you look on the paper from yesterday that I gave you that has the geometries, how many geometries are there?
24.
No, there are, how many? Versante?
18.
15.
12.
Shh. Hello. There are 15 geometries. So we've only used 2 of the 15 for this molecule. You can find the other 13 in other molecules, obviously. But we're just trying to help you understand that these geometries are used. Now, why is it difficult to draw these and show the geometries? Anybody? Why is it difficult to draw these and show the geometries? What is the geometry of the tetrahedral? You might know what the angle is for tetrahedral?
90 degrees.
No.
109.
109. So, yeah. What? Jimmy, what would you need to use to draw a 109-degree angle here? A protractor.
Did I get points for that too?
Did they use a protractor here?
No.
No, they did not use a protractor here. Now, most of your molecular geometry modeling, Jaden, most of your molecular geometry modeling is done with computers. Even when I was in school, we relied on computer modeling and not like drawing to visualize these. Because it's just a lot easier for the computer to be more accurate. And if you're building something, you want the plan to be as accurate as possible, because if it's not, what you build is not going to fit, and that's gonna be a problem.
Function to distinguish between normal and abnormal cellular components and between self and non-self. As an example, when a thorn gets stuck in the body of the immune cells are able to recognize the thorn as a foreign object.
That when some cancers form, the body doesn't try to eradicate or kill them. Now, alcohol is a good example of the reason for this. Alcohol use in cancer. Now, if you drink 1 drink a day, your body, your liver is most likely going to be able to get that toxin out. The problem is if you're drinking like 12 to 15 beverages a day, or pure alcohol, that would be like bourbon, because they say the greater the concentration, the more problems that can occur. So what'll happen then is that the body will start trying to isolate these toxins other places. And that's when these cancers can form. Now, when they go and actually attack your organs, that's the last step typically. They have formed other places, and then the last place they go is the organ. And once they get in the organ, there's pretty much nothing else they can do, and you die. Doctor, raise your hand, and they're testing you, and and they find that you have some lung cancer, the doctor says, do you smoke cigarettes? And you say yes, what is he going to tell you to do?
Stop smoking. Don't smoke cigarettes, bro.
Stop smoking cigarettes, right? So, now, I can take some points on the side with the information about the shapes. What were the total groups around ozone 03? We said yesterday?
3.
There were 3?
Yeah.
Because there was a double bond there, right?
Yeah.
Remember drawing that? So how many did we have around ozone?
So we had 4.
There were 4 around ozone?
That was 4.
And how many were around the other one? CH?
2, 6.
No, there were 4 around CHCl3. Has 3 groups. 1, 2, 3. Now when we start looking at the groups, it is important when we look at hybridization. They'll ask you for like the hybridization of a long molecule like mustard gas, like on a test. So we're trying to help you understand the hybridization just a little bit. So if we look at the sheet that I gave you today, right? You came in, it shows you the hybridization, and it says the concept of hybridization was introduced because it was the best explanation for the fact that all CH bonds in molecules like methane were identical. So if you look at the first one, does everybody see the triple bond? In math, specifically geometry, what horizontal plane is that called?
X.
It's the X. And that's what you see right here. See how you've got the triple bond? It's only seen in the X. So that's going to be an SP. This P is associated with the X. The P is associated with the X. Now if we look at the double bond, you'll see the drawing here, you have the Y comes into play. What is the Y? The vertical, right up and down. So that's when you have an SP2 because you have the X and the Y. Everybody see that? SP2. And then the last one, you have the single bonds, all single bonds, and that's where you get the Z, the 3-dimensional comes out. It's much more difficult to draw that. They've shown you at the bottom here. So when you have 4 single bonds, that's going to be a hybrid of SP3. Now these are the 3 possibilities for typically organic substances like carbon. You can get into the D hybrids. We don't typically talk about those unless you go into like industrial chemistry where you're dealing with metals. And we're not going to go there because most people are looking to make money or go into medicine, and you'll see these in medicine more. So if you look up here, the methane, he was just showing you there, correction, the methanol. When you look at these, if you don't see any double bonds, these are all going to be SP what?
3.
SP3. This is SP3, 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 and so forth, because there's no double bonds there. Or remind, if you see a double bond, then you know it's going to be SP2. If you see a triple bond, it's going to be SP, just SP1, right? So we do still have to figure out the molecular geometries. There's not one for chlorine because it's just attached. So the first one we're going to look at here is the carbon. It's tetrahedral because you have the X's around it. There's 1, 2, 3, 4. Does everybody see that? So it's AX4. The next one, 1, 2, 3, 4, AX4. Now the sulfur has 2 lone pairs. So that's going to be 1, 2, AX2, N2, because you have the 2 lone pairs there. And it's going to be bent. We just look up on the chart and it tells us it's bent. Then back to the tetrahedral, carbon, another carbon, AX4, and then chlorine. This is mustard gas. If you're trying to build something, plan first. You have to use a plan. You're going to build a building, you're going to build a molecule. You need to know what it looks like. Now, is drawing this going to be difficult? Yes, why? Because you have the exact bond angle. If you look at tetrahedral, the bond angle for tetrahedral is 109, and then bent is 109 as well, so you have to pull out your protractor and do that. Most of this is done on a computer. And we're just trying to explain to you so when you see the computer model, they're not going to tell you it's 109. They're just going to show you what it looks like. But you need to understand where these angles come from. it was originally drawn like you see on that page. Germany first used mustard gas on which country? No. 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 World War I was considered to be the chemical war. No.
Germany.
No.
The United States.
Why would Germany use it on Germany?
The United States.
No.
Oh, I thought that was Pearl
No.
Japan.
No.
Don't
No.
give us the answer until we get it. France.
No.
Oh, I got it.
China.
Lithuania.
No. I'll give you a hint.
Finland.
I'll give you a hint. The Pope.
Mexico. Spain.
No.
Italy.
Italy.
What?
Budget for textbooks completely. Most schools are already using like digital textbooks. That's money that has to be paid to the textbook companies. So online now, they're kind of relying. Google is like the big pusher behind this. They're saying you can find 3 resources that are correct on the topic, then it's reliable. So up here, the basic assumption of Vesper theory, it tells you the answer right there. So they're trying to look for ways to save money, and that's one way that we're doing it, but I still can find reliable resources to provide you to look for the answers on the internet, as you can see there.